very much. Thank you for the invitation to speak, and thanks for coming. So I work in algebraic number theory, and I work in the part of algebraic number theory that's called the Langlands program, and that is about building reciprocity laws and connecting number theory to other parts of mathematics, such as harmonic analysis and representation theory. And so I want to start out by just giving a very basic example of a reciprocity law, the kind of connection that we're looking for. And so the first example of such a reciprocity law is quadratic reciprocity. And so you could ask the following question. Well, first of all, just when you first start thinking about properties of whole numbers, a very basic question that can come up is what numbers can be perfect squares? What can the last digit of a perfect square be? And if you think about it, okay, you can have 1, 4, 6, 9, 5, 0, but you can never have 2, 3, 7, or 8. And so, it seems like there's a pattern there. You can ask a more general question. You can ask, okay, what can the last digit of a perfect square be? Not in base 10, but in base p, where p is some large prime number. So, for example, if, say, q was some other prime number, you could ask about the equation x squared minus q and whether that has solutions, but not sort of on the nose, not trying to solve this equation on the nose, but rather, can you find a whole number x such that x squared minus q is some multiple of a prime number p? So p and q are primes. So you can ask this kind of question, or alternatively, how does the number of solutions to this equation modulo p vary as p varies? And it turns out that quadratic reciprocity tells you precisely that the number of solutions can be 0 or 2, and the fact that it's 0 or 2 depends only on sort of what the residue of p is when you divide it by q. Well, really by 4q. So on p modulo 4q. So this is a very simple kind of reciprocity law that encodes the number of solutions to a quadratic equation just in one variable. And the number of solutions modulo p as p varies is given by p modulo 4q. And this kind of reciprocity law was generalized in the first half of the 20th century, and that was known as class field theory. That was a very exciting achievement. So this is maybe the first example that I want to give. But then in the 1950s, Eichler wrote down a different kind of reciprocity law. So this was maybe the next really spectacular development, reciprocity law involving an equation, so a cubic equation in two variables. So I'll say this is a reciprocity law for the following. So the cubic equation would be y squared plus y equals x cubed minus x squared. And what you're looking at is the number of solutions in the number of solutions, but again, modulo p. And let's say that this has np solutions. So the question is, how does np vary? And it turns out that, well, you can compute, say, you can look at solutions mod 5, and you get 4 solutions. You can look at mod 7, and so on. And as you compute small values, what you see is that the number of solutions is roughly as large as the prime number p. So here we just had 0 or 2 solutions. Here you can, for large primes, you can have lots and lots of solutions. But it turns out that the error term, so this quantity p minus np, can be described by a reciprocity law. And I'll give you sort of a very basic version of this, and then I'll explain what's underneath it. So the idea is that this error can be recovered as the coefficients of the following power series expansion. So we're going to take an infinite product, q times the product from 1 to infinity, 1 minus q to the n, squared, 1 minus q to the 11n squared. And you expand this out. This is a power series in q. Starts with q to the 1, so an q to the n. So you have this kind of power series expansion. And it turns out that when p is a prime number, you have the reciprocity law, ap is equal to p minus np. All right. And so as you expand this power series, you can compute the coefficients. And for instance, you can check that the fifth coefficient is 1, which matches 5 minus 4. All right. So this is a kind of next level of reciprocity law. It's giving you something about the number of solutions of a cubic equation in 2 variables. But the really interesting thing is that there's sort of a lot of math that's hidden underneath this. So I want to try and explain sort of what the 2 objects mean. So what does the cubic equation mean? What does this power series mean? And so that is a more sophisticated version of the reciprocity law. And that is, let's say, I could say the statement that elliptic curves are modular. So I need to talk about the 2 objects that show up. So first of all, this equation, this cubic equation with integer coefficients, this represents an elliptic curve E over Q. So an elliptic curve is a projective smooth curve of genus 1 together with a distinguished point, a point at infinity. And if you forget about the point at infinity, then you can describe this elliptic curve by means of a cubic equation, for example, this one. And so this cubic equation is really this kind of elliptic curve. And the statement that elliptic curves are modular is the statement that you can extract from the elliptic curve a number theoretic object, a Galois representation, and you can show that this is the same as the number theoretic object, or the Galois representation that you can extract from some other side, the side of a modular form. So a Galois representation is, first of all, a representation of the absolute Galois group of Q. So what you want to look at is, OK, you have the rational numbers. If you adjoin to the rational numbers solutions to polynomial equations, then what you get are algebraic numbers. And algebraic numbers have lots of symmetries. And if you look at sort of all the symmetries of all algebraic numbers, then you get this kind of Galois group. And concretely what this is an inverse limit of the Galois groups of all the finite extensions of Q. And so this is a very big profinite group. It has a complicated structure. Topologically, it's something like a Cantor set. And it turns out that we can use 2-dimensional representations of this kind of Galois group to remember some information coming from elliptic curves and also coming from this kind of power series that I'll talk about in a minute. So let me just say, so what we are looking for is Galois representations that are 2-dimensional. So I'll say here, this is what we're interested in. And they are valued, so sort of everything is constructed really in terms of congruences mod p or mod p to the n. It turns out these Galois representations will be valued in QP, where QP is the completion of the field of rational numbers, but not with respect to the usual absolute value, because then you would get the field of real numbers, but rather this is the completion with respect to the p-adic absolute value. That's precisely when you say that two rational numbers are close if they are congruent modulo a high power of p. So if their difference is a multiple of a large power of p. And so it turns out that does satisfy the triangle inequality. It does give you an absolute value, and if you take the completion with respect to that, what you get is this field QP. So the elliptic curve, so for getting the point at infinity, is just given by this cubic equation. There's a kind of, maybe this is the algebraic way of thinking about the elliptic curve. There's a geometric way of thinking about it as well. Let's say if I take the underlying Riemann surface, I said it's genus 1. The underlying Riemann surface is a torus. C modulo some lattice looks something like this. So we have some point at infinity. And then, yeah, so it's a torus. And something that you can see from the geometric picture, and that still exists from this more algebraic description, but it's harder to see, is that this is not just a curve, but it also has a group structure. And the group structure on the underlying Riemann surface is just induced from addition on complex numbers. So you can define what it means to add points on this torus, and it's just sort of you add complex numbers, but modulo this lattice lambda. And so in order to extract some number theoretic information from the elliptic curve, what you need to do is use the fact that it's a curve defined over Q, but also use the fact that it has a group structure. And the way you do it is you look at the p to the n torsion points on the elliptic curve for varying n. So what do these mean? So points on the elliptic curve such that if you multiply them by p to the n, you get to the origin. So the point at infinity is identified to the origin in this picture. And the p to the n torsion points, just geometrically, they look like z mod p to the n z squared. So that's sort of abstractly what they're isomorphic to, but they have extra structure. And the extra structure comes from the fact that you have this elliptic curve defined over Q, and so you can say, you can define the group structure over Q as well. So you could have, say, points x1, y1, x2, y2, and adding them up would be given by some polynomials in x1, y1, x2, and y2. And so that means that when you try to find p to the n torsion points, what you're doing is just solving a bunch of polynomial equations. And that means that the coordinates of the p to the n torsion points are algebraic. And because of this, they come with these extra symmetries. They come with an action of this absolute Galois group. And so I'll call this G sub q. This is the absolute Galois group of q. And so this module has this extra structure, this action of the Galois group. And so the Galois representation attached to an elliptic curve, I'll call that rho e. So this is exactly the Galois action on the p to the n torsion points as n varies. And it turns out that as n varies and goes to infinity, these actions are compatible. And what you get is an action on the inverse limit. So this is the same as GL2 of the inverse limit with respect to n of z mod p to the n z. And so it turns out, so you can define this inverse limit to be zp, and then that zp is identified exactly with the ring of integers inside the field qp of p-adic numbers. So this is GL2 of zp, where these are now p-adic integers. And so to get qp, all you need to do is invert p. All right. So you use the fact that you have a group structure defined over Q to construct a Galois representation from the elliptic curve E. And so this seems pretty specific to this context where we're looking at an elliptic curve. And you have all this, to use as a crutch. But it turns out, so I want to make this remark, there is a general machinery that will give you lots and lots of Galois representations. And for that, maybe it's useful to think about what z mod p to the n z squared represents in terms of the elliptic curve. it's exactly the first singular homology of the elliptic curve with coefficients in z mod p to the nz. So, so what we've done here is we've put a Galois action on this first homology. So if you work dually, you could work with cohomology, and then basically you're looking for a way of putting a Galois action on the cohomology of some algebraic variety defined over Q, and that's exactly what étale cohomology does for you, as long as you change your coefficients appropriately. So I'll just say that étale cohomology, which was developed by Grothendieck, gives GQ action on HI of, so the singular or Betty cohomology of an algebraic variety, so as long as you extend your coefficients to QP, and X is some algebraic variety defined over the field of rational numbers. So it's given by the solution to some finite number of polynomial equations, for example. So whenever you have something like this and you take Betty cohomology and you extend your coefficients to QP, you're going to have a way of getting Galois representations. And so I guess on this side of the reciprocity law, this cubic equation represents an elliptic curve, and then you use this concrete version of étale cohomology to get the Galois representation. So now I want to talk about the other side and what this infinite product represents, and talk about how to construct a Galois representation from this infinite product. And it's going to be more vague, so I'm not going to give such a concrete way of doing it. But so the first thing that I want to say is I said there rho f. So what we have is f is a modular form. So this is really an object that lives in the world of harmonic analysis. It's a holomorphic function on the upper half complex plane. So a set of complex numbers that have strictly positive imaginary part, and also satisfying many symmetries. And maybe I'll be more precise about what these symmetries are later on. I'll just say that one of these symmetries is invariance under sending z to z plus 1, which means that you can write such a holomorphic function in terms of its Fourier expansion. And so if you take q to be the parameter e to the 2 pi I z, then such a modular form is given by a Fourier expansion, which is exactly this type of power series in Q. And so this particular infinite product is really the Fourier expansion of a modular form, of a very specific modular form. So a function on the upper half plane satisfying a specific set of symmetries. All right. And so to tell you a little bit more about how to understand modular forms, first I need to talk about the space that the modular forms live on. So the upper half plane can be endowed with a hyperbolic metric, and its group of isometries under this hyperbolic metric is SL2R. So H has an action of the group SL2R. These are known, so kind of the action of a matrix is in SL2R on the upper half plane is known as a Möbius transformation. So if you've heard of those, maybe I'll say another way of thinking about this action is you can embed, if you'd like, the upper half complex plane into P1 over C, the flag variety that parameterizes lines inside a two-dimensional complex vector space. And this has an action, natural action of GL2C, and the action of SL2R on the upper half plane is exactly the restriction of the action of GL2C on P1 of C. All right, so you have something like this, and because of this, because of this, you can you can view H, is there a question? Sorry. You can view H really as a quotient of the real points of the group SL2 by the stabilizer of any one point on the upper half plane. That's the point I. So for example, I could take the point I here. The stabilizer would be SO2R. Okay, so there's some hint at what the underlying structure of the upper half plane is. You can think of it as this kind of quotient, and I should say that if you look at it on this side, then a priori what you see is just that you have the structure of a real manifold. So you've started with some reductive group over Q, for example, SL2. You can take the real points of that, and you can take the quotient of that by a maximal compact subgroup. And so a priori, so what you get is called a symmetric domain for that group. And a priori, it just has the structure of a real manifold. On the other hand, if you look on this other side, the upper half plane has a natural complex structure. And so to study modular forms, which are these, you can think of them as giving rise to these Q expansions, these power series in Q. It turns out you have to think a little bit about the upper half plane. And in the special case of modular forms, there's more structure hiding underneath. There's a connection to this connected reductive group SL2. And then there's a natural complex structure that you can put on the upper half plane that's not necessarily obvious from that description. So maybe I'll talk about the symmetries that F needs to satisfy. So the symmetries are under the group, well, SL2Z lives inside SL2R, so it acts on the upper half plane. And inside here, you can define congruent subgroups. So the particular one that I'm going to take is going to be gamma 0, 11. This is a subgroup defined by a congruence relation. It's a subgroup of matrices that are in SL2Z, which satisfy the property that they are congruent to upper triangular matrices modulo 11. So it turns out that the particular modular form that I wrote down has symmetry specifically under this subgroup. And so in general, you could have lots of other congruent subgroups inside SL2Z. But for this particular one, we're going to work with gamma 0, 11. Maybe I'll call this gamma. And so it turns out that the symmetries of F are sort of designed precisely to make F descend to a holomorphic differential on the quotient of H by this gamma. So F descends to a holomorphic differential on the quotient H modulo gamma. And maybe I want to draw a picture. So I won't draw a picture of H mod gamma, but just maybe of H mod SL2Z. So in order to do that, what you want to do is draw a fundamental domain for the action of SL2Z on the upper half plane. And what this fundamental domain looks like is something like this, where here you have a sixth root of unity. Here you have a cube root of unity. These are vertical lines. This is I. And so this is a fundamental domain. And in order to think about the quotient H mod SL2Z, what you need to do is identify this side with this side, and this side with this one. And then your quotient looks something like this. So it's basically, it's not compact. It's like the punctured Riemann sphere, except it's not really a manifold. It has a couple of orbifold points around I and rho. But otherwise, it looks something like this. And H modulo gamma 0, 11 possibly look like a cover, maybe with higher genus. So maybe something like this. So the smaller your gamma, the more congruence relations you impose, the bigger your space, you get some covering. All right, so the modular form F, really its symmetries allow you to think of it as a holomorphic differential on this space. And because H has a complex structure, the quotient H mod gamma also, it turns out you can endow that with a complex structure as well. So this is a Riemann surface. And now the more sort of striking thing is that it's not just that, but it turns out to be the underlying Riemann surface to an algebraic curve that's actually defined over Q. So, so let me write that. So where y gamma is defined over Q, so maybe not necessarily an elliptic curve, so not genus 1, depends on really what gamma is, but so some curve. It's not projective over Q, sorry. And I should tell you why this happens. So this has to do with the fact that we have a complex structure here. But really, sort of, the reason why the curve is actually defined over Q is that you can think of the upper half plane. First of all, you can think of it as a moduli of complex structures that you can put on a two-dimensional real vector space. And if you think a bit more about that, that would be the same as a moduli of Hodge structures that you can put on a two-dimensional real vector space. And then it turns out that you can interpret the quotients of H by gamma as moduli of elliptic curves over C, possibly equipped with extra structures. And so you can define the moduli problem elliptic curves with extra structures over Q, and that's how you can show that it actually comes from a curve defined over Q. And so the idea is to think of this H as parametrizing Hodge structures of elliptic curves. And then you want to think of this embedding that I drew here, the map from H to P1 of C, as the map that will take the Hodge decomposition to the Hodge filtration. So the Hodge filtration on this two-dimensional, say the Betty cohomology, or de Rham cohomology, say, of an elliptic curve, would just consist of a one-dimensional subspace inside a two-dimensional one, and that's exactly what this P1 of C parameterizes, lines inside a two-dimensional complex vector space. So I guess the point is to think of this map as taking the Hodge decomposition or Hodge structure to the Hodge de Rham filtration. All right, so that's the story. And so F, you think of it as giving rise to a differential, omega F. And because of the Hodge decomposition for y gamma, or maybe some refinement because y gamma is not compact, you can think of it as contributing really to the Betty cohomology of this curve defined over Q. And then you have to see that the Betty cohomology has, say, you can take it with rational coefficients, and then if you can, and you take your scalars and you extend them a different way, and so you can extend them to QP, and then you can work with the étale cohomology of the curve. So roughly, because you have, because these quotients, H mod gamma, really have this structure, you have access to étale cohomology, and because of that, you can construct the Galois representation attached to a modular form F. So you can construct rho F this way. And so it's more vague, and it uses this étale cohomology machinery. And there's a specific sense in which you can trace the modular form F through all these spaces. And the way you do it is basically there are lots and lots of, so these spaces have lots and lots of symmetries. There are some operators that are called Hecke operators that act on everything in sight, that act as correspondences. And what you're tracing through is really systems of eigenvalues of all these operators. So you're keeping track of spectral data, and you're cutting out some generalized eigenspace, or eigenspace corresponding to a certain system of eigenvalues, and that's where you see this Galois representation attached to the modular form F. All right. And so maybe I want to talk a little bit. So the reciprocity law the sophisticated version of the reciprocity law says that you have an isomorphism between the Galois representation coming from this cubic equation and the Galois representation coming from the modular form with that specific power series expansion. So the reciprocity law was this one. And so now you have some hint about what these objects are, how they're constructed. And so maybe I want to talk a little bit about consequences. And there are sort of two major consequences in both directions. And so the first one is, let's say, the fact that if you have an elliptic curve, then you can relate that to a modular form. So in that direction, the famous consequence is Fermat's last theorem that was proved in '95 by Andrew Wiles, and that relies on the so-called Taylor-Wiles method. The Taylor-Wiles method is a method of sort of setting up mod p congruences and studying congruences both on the side of Galois representations and also on the side of modular forms, mod p or mod p to the n. And the idea is to kind of use some non-trivial solution to Fermat's equation to cook up an elliptic curve that cannot possibly come from a modular form. So this is a consequence of the fact that if you have E, you can go to F. And so, you're relating two worlds, this kind of number theoretic world and the world of harmonic analysis. Neither one of them is really easier to deal with. But in this direction, sort of, you can transfer one question and make it approachable. And in the other direction, a question about the modular form F that is hard to answer within the world of the modular form, but that becomes approachable once you go to the world of elliptic curves or algebraic geometry, is is the Ramanujan conjecture. So that's something that I want to say more about. So the Ramanujan conjecture for F, and so I should tell you what that says. Well, good pronouncement. Thank you. So it says that if you look at some prime number L and you look at the Lth Fourier coefficient of the modular form, then, so for this specific modular form, it's saying that this is less than 2 times the square root of L. So, and so this is something that, so a statement about the growth rate of the Fourier coefficients of the modular form F. And it doesn't seem easy to prove just on the side of the modular form, but you can transfer it to the side of the elliptic curve. And so what the more sophisticated version of the reciprocity law says is the following. So first of all, you can relate AL to the Galois representation attached to the modular form F in the following way. So it turns out that these Fourier coefficients, which are also, in this special case, exactly eigenvalues, so spectral data, can be identified with the trace of the Galois representation attached to the modular form F, evaluated at a specific element, which is the Frobenius at L. So I'll take L to not be P and to not be 11. 11 is sort of a weird prime for the modular form F and also for that cubic equation. So if you take L to be different from P or from 11, then it turns out that you can really probe the absolute Galois group of Q from the point of view of this representation by the Frobenius at L. So these are elements that are really, so these are really elements in the absolute Galois group of the finite field with L elements. It's an automorphism that will send x to the L. And so it turns out that there's a way of lifting these and thinking of them as elements in the Galois group of Q, at least from the point of view of this particular Galois representation. So this is well defined. And then what the reciprocity law is saying that this is the same as the trace of rho E on the Frobenius at L. So this Frobenius at L element, this is thought of as generating this Galois group. So the absolute Galois group of a finite field is really just generated by this one element. You can evaluate the Galois representation attached to elliptic curve on this. And it turns out that you can reinterpret this via some sort of Lefschetz counting point formula as as L minus n sub L. So L, the prime number that you start with, and n sub L was really the number of solutions mod L to this cubic equation. So this error term that I said was encoded in the Fourier coefficients of the modular form. And just to explain sort of what's happening here, the point is that you can think of your elliptic curve, so for instance that cubic equation, as not being a cubic equation over Q, but rather you can think about this as defining an elliptic curve. So you can think of the equation mod L, you can think of this as defining an elliptic curve over FL. And whenever L is not 11, it turns out that this is actually smooth. So it does give an elliptic curve over the finite field with L elements. And then this will have an action of this Frobenius element. And what you are computing here is roughly the trace of that Frobenius element acting on the H1 of the elliptic curve. And so the Lefschetz counting point formula comes from looking at H0 and H2, which are easier to understand. And then you compare it to the number of fixed points. And the number of fixed points are exactly points that are fixed by sending their coordinates, say x1, y1 to x1 to the L, y1 to the L. And those are exactly the points of the elliptic curve that are actually defined over the ground field, the field with L elements. So, so the idea is to think of this as sort of something coming from H1 in the sense of étale cohomology, so in the sense of this mysterious cohomology theory. OK, and then the point is that to get the bound AL in absolute value less than twice the square root of L, what you need to do is instead get a bound on this side. And for that, the following is a consequence of the Weil conjectures. So let's say X over FL is a smooth projective curve. So for example, it could be our elliptic curve E. And then you can look at HI of X. So this étale cohomology with QP coefficients, this has, because the étale cohomology comes with a Galois action, this has the action of the Frobenius at L. And what the Weil conjectures tell you is that the eigenvalues of the Frobenius at L are actually algebraic numbers. And if you embed them into the complex numbers in any way, then their absolute value is going to be determined just by the degree of the cohomology group that you're in. So the eigenvalues of the Frobenius at L have absolute value always L to the I over 2. And so this is how now you can get the right bound. This is, you're looking at the Frobenius at L acting on H1 of the elliptic curve. And so the absolute value of the two eigenvalues will be square root of L. And so the trace is the sum of the eigenvalues that's less than twice the square root of L. All right, and so you get the bound on this side. And that's another example of what the reciprocity law is good for. I should say this was all proved. So most of what I've told you was already known since the 70s and largely done by Deligne, including the Weil conjectures and the proof of the Weil conjectures and this bound, the Ramanujan conjecture. OK, but so since then, people have been trying to generalize things to higher dimensions. And so I want to end by thinking about sort of the more general picture. And there are sort of two things that you may want to generalize. One of understanding sort of analogues, higher dimensional analogues of modular forms, and relating them to Galois representations. And another one is sort of understanding a generalization of the Taylor-Wiles method, which is this method that uses congruences and that starts with a Galois representation, such as the one coming from the elliptic curve E, and tries to connect it to a modular form. So I'm going to start talking about the higher dimensional version from the point of view of sort of kind of generalizations on the automorphic, on the modular form side. And so what I'm going to take is maybe I'll take G to be a connected reductive group over Q. And attached to G, you can form the symmetric domain by taking the quotient of the group of real points by a maximal compact subgroup. So for SL2, this was the upper half plane. For other groups, for example, if I took SL2 over an imaginary quadratic field, so for instance, the restriction of scalars, but I can just think of it as SL2 over Q adjoint I, then it turns out that X can be identified with hyperbolic 3 space. So there are some instances where you don't get something with a complex structure. Here you can just use the formula and see that what you should get here is a real manifold of dimension 3. So it doesn't have any hope for having a complex structure. And then if you take gamma inside G of Q, some congruent subgroup, so something that's cut out by congruences, and you look at the quotient X sub gamma, this is defined as the quotient X mod gamma. These are locally symmetric spaces for the groups G, for the group G, in the case when G is SL2 over an imaginary quadratic field. The locally symmetric spaces are arithmetic hyperbolic 3 manifolds. So again, you don't have an algebraic structure the way you did for the quotients Y gamma, which were these curves defined over Q, modular curves. So you don't always have an algebraic structure. That's one obstruction to generalizing things. I'll just say, however, in some cases, so in the case where you can interpret the symmetric domain as a sort of moduli space of Hodge structures of abelian varieties, so generalization from the setting of the upper half plane where you think of them as moduli spaces of Hodge structures of elliptic curves, you can get an algebraic structure. So if G is, for instance, GSP2G, or a unitary group, then you do get an algebraic structure. And in that case, so X gamma has an algebraic structure, and in that case, the X gammas are called Shimura varieties. So they're going to really be algebraic varieties that are defined over Q or over some finite extension of Q, so over some number field. And in that case, it's still possible to generalize the story that I talked about here. And so that's something that people have been doing for the past maybe, well, in the, say, 30 years or so. And it's been quite successful. So maybe I want to just give you an example. So I talked about the Ramanujan conjecture for this special case, this modular form F. So there is a generalization of this conjecture to higher dimensions. It's called the Ramanujan-Peterson conjecture. I want to tell you what's known about this. So maybe I'll say this is theorem 1. And so in order to phrase it, I need to use some technical words, but I'll try to say what they mean. And so I'll take pi to be a cuspidal automorphic representation of GLN. Let's say over some F, which is a CM field. So the composition of a totally real extension of Q with an imaginary quadratic extension. All right. So let's say that you have something like this. This is going to be a higher dimensional version, higher dimensional generalization of this notion of a modular form. And you need to have some technical conditions. You need to put some technical conditions on this pi. And one condition that I'll put that's technical is I want pi to be regular algebraic. And what this condition means is roughly well, it will tell you that, the way that we thought of f as giving rise to a differential, a holomorphic differential on the y gammas on the modular curve, and therefore we saw that it contributed to the p-adic cohomology of the modular curves. You can ask for something that will contribute to the cohomology of the corresponding locally symmetric space, and that's what this technical condition that's regular algebraic will achieve. So you will see it in the cohomology of the relevant locally symmetric space. And you also, maybe the problem is that that locally symmetric space may not actually have an algebraic structure. And if you want to find a direct generalization, you want to go to the world of algebraic geometry. Maybe you want to be able to relate to one of these cases. And then that's achieved by giving pi an extra condition. So I'll say that pi is self-dual. So if it has this sort of extra symmetry, then you can relate it to an automorphic representation, say, coming from a unitary group. And you can relate it to Shimura variety, so the world of algebraic geometry, where you have access to étale cohomology and the Weil conjectures. And so under these conditions, you know that pi satisfies the analog of the Ramanujan-Peterson conjecture. So I'll say pi, maybe I'll just say this. Pi satisfies the Ramanujan-Peterson conjecture at all finite places. And so what this is saying is that you can look at, so the modular form is really sort of one object, whereas this is a representation. You want to think of the modular form as being just one vector inside a big automorphic representation. But from the representation theoretic point of view, you want to decompose this somehow into local components that have to do with these sort of Fourier coefficients given by prime numbers. And those local components, those have to be sort of only slightly, so in terms of their matrix coefficients, those have to be tempered. And that's only slightly weaker than saying that the matrix coefficients are square integrable. So there's a precise notion for what you want here. And I'll say that in this generality, so using this kind of template in the case of the modular form f, but using unitary Shimura varieties, this was proved by Harris-Taylor and Clausel, Shin, and one last case was done in my thesis. All right, and so that's something that we know how to do for this direct generalization of a notion of a modular form. And as I said, this has to do with automorphic representations that contribute to the cohomology of locally symmetric space x gamma, and maybe with complex coefficients or with QP coefficients. So something like this. So this theorem is about the cohomology of such spaces, but with complex coefficients or coefficients in QP. Right, like this sort of condition exactly allows you to understand the singular cohomology or the p-adic cohomology of these spaces. This kind of condition takes you here. And something else that's been happening lately is that people have been starting to understand not just the cohomology of these spaces with characteristic zero coefficients, but also the cohomology of the spaces with torsion coefficients. So I could put FL coefficients. And so, what can one do in the case of torsion coefficients? So that's a different story that I want to talk about. First of all, I should say sort of this is the kind of the last thing, one of the last things that you can prove about a representation satisfying these conditions. And along the way, you construct Galois representations and so on. And people have been very successful lately in constructing Galois representations, even so in higher dimensions, and even in the case where the spaces don't have an algebraic structure. And so in particular, Harris, Land, Taylor, and Thorne can understand the cohomology of such a, say, arithmetic hyperbolic 3-manifold with characteristic 0 coefficients. And Scholze and more recently Boxer have constructed Galois representations even in the case of torsion coefficients. The kind of question that I want to end with is not really directly about Galois representations, but rather it's a generalization, or it's some sort of torsion analog of the kinds of ideas that you see here. And for that, I want to comment that kind of the key thing in proving this kind of theorem is that the representation pi is locally generic. So this is a technical condition, but it's saying that these local representations that make up the big automorphic representation pi are generic, and so in some sense as far away as possible from the trivial representation. And when you start with something like this, you get this kind of condition for free. And then what you need to do is, well, you just use this together with the Weil conjectures. The Weil conjectures gives you very precise information about what degree, so not just the fact that you contribute to cohomology in some degree, but it tells you what degree you contribute in. It's typically going to be the middle degree. And so really sort of this together with the Weil conjectures allow you to prove this bound that you want, the one that the Ramanujan-Peterson conjecture asks you to do. And at the same time, it sort of, these two things guarantee that the representation pi does contribute to the middle degree cohomology. And so I want to end with talking about torsion from the point of view of controlling what degree torsion contributes to. And so the question would be, what about torsion? And I want to say that, I mentioned the Taylor-Wiles method. It's about going the other way from the Galois side, tracing back to classes in the cohomology of these spaces. And there's a recent strategy due to Caligari and Garrity, a strategy for extending the Taylor-Wiles method in higher dimensions, especially in the case where your spaces are higher dimensional and you can have cohomology in lots of degrees. So they outline a strategy for extending the Taylor-Wiles method, say to the case of GLN, to higher dimensions. And what they need for their strategy to work, well, they need several things, but one of the things that they need is they need to know that non-degenerate torsion classes are concentrated in 1 degree. So for instance, if you could say that sort of non-degenerate torsion only occurs in the middle degree, then you'd be in business. In general, say for a group like GLN or SL2 over an imaginary quadratic field, they give you a precise range of degrees where you need torsion to occur in. So this is the kind of result that we can prove now about torsion classes, at least in the case of compact Shimura varieties. So this would be the second theorem that I want to mention. So I'll say X gamma be a compact, so not like the modular curves. You actually want it to be compact, and you want it to be the locally symmetric space coming from a unitary group. And you have an algebraic structure, so you have a compact unitary Shimura variety. And then the question is about the cohomology of such a space with torsion coefficients. And so again, you understand classes by really looking at all these extra symmetries and taking really systems of Hecke eigenvalues. So I'll say let psi in here be a system of Hecke eigenvalues, well, really an eigenvector that has attached to it a system of Hecke eigenvalues. And the kind of theorem that we prove is exactly relating genericity on the representation theoretic side to the statement that you are only occur in the middle degree. So the kind of information that you could extract there as well. So if psi is sufficiently generic, it's a technical condition, but it can be made precise, and it matches, it's a mod L version of the kind of condition you have there, then psi occurs in the middle degree. All right. And this is very recent joint work with Peter Scholze. Yes. Yes. Only in the middle degree. That's right. So it cannot occur outside the middle degree.
But in the other case, absolutely critical issue is custodiality.
Yes.
In order for that to happen. Now you've thrown that away.
That's true. Yes.
That's still true.
Yes.
This is compact.
I mean, some.
Usually when you're looking at classical forms of a compact, you make a transfer, you might be looking to Eisenstein.
That's true. So I mean, you could have a reducible Galois representation attached to it, as long as it was generic.
Okay. Are you assuming some? Okay.
I mean, there is an assumption. This genericity. Yeah. I mean, otherwise it would be quite a. Yeah. I mean, in general, there can be lots of torsion. So the question is whether you can sort of put some condition on the torsion classes that will ensure that, you kind of only see the middle degree. So I just want to end with drawing.
Assuming is the generic assumption something like particular function assumption or something else?
Well, it's mod L. So, but it's sort of saying that any lift to characteristic 0 has to be a generic principal series representation at some prime number. So the way that we prove this is really using p-adic geometry and a p-adic version of Hodge theory. So Hodge theory came up earlier in the talk when we were thinking about sort of understanding modular forms and how they contribute to p-adic cohomology. This theorem is proved using a p-adic version of Hodge theory. So I just want to draw a complex picture and a p-adic picture that's analogous to it, and I'll end with that. And so in the case of modular curves, we were looking at these modular curves as complex analytic spaces. And then those would be identified with these quotients H mod gamma. So the upper half plane is a universal covering space of these complex analytic spaces coming from the Y gammas. And then the upper half plane was equipped with this embedding into P1 of C. And so all the symmetries really came from the action of SL2R here and the action of GL2C here. Now, sort of this map is equivariant for these two actions. And this kind of picture has been used in the past to understand properties of modular forms. For instance, to kind of, show that they have the right integrality properties. That's kind of the complex picture. It's been useful in the past. The picture that we use is we will think of Y gamma as a p-adic analytic space, more precisely an adic space in the sense of Huber. And we need to take some big cover of this space. And what this cover does is sort of here you would have, you parameterize elliptic curves. And at this point here, you're trivializing the de Rham cohomology. And what this map does is it's taking the Hodge decomposition to the Hodge filtration. We're going to take some big cover that's going to amount to imposing more and more congruences to our subgroups. So we're taking smaller and smaller subgroups where we're asking them to be congruent to 1 mod p to the n for larger and larger n. What the effect on the level of the moduli problem is that here you parameterize elliptic curves, possibly with extra structures. Here you parameterize elliptic curves with extra structures, and you're basically trivializing the H1 étale of that elliptic curve. And once you've done that, it turns out that there exists a period morphism that's similar to this one. It goes to something sort of simpler. then this space is very, very complicated. It's a perfectoid modular curve, kind of looks like a fractal. This space looks nicer, and it's just P1 of Cp, where Cp is Qp, algebraically closed and p-adically complete. And this comes from the Hodge-Tate decomposition. That's a decomposition on the étale cohomology of the elliptic curve that's in some sense dual to the de Rham filtration. So this is called the Hodge-Tate period morphism. And so the way that we prove the theorem is we compute, instead of the cohomology of this space, we compute the cohomology of this. And rather, really, we understand first the fibers, and then we compute the cohomology of this together with equivariant sheaves. And of course, all of this is equivariant for the action of, say, GL2 QP. All right, so I'll end here. Thank you.